Okay, hello everyone, and welcome back to your YouTube channel. And welcome to this amazing and very practical video today. As you must be aware, I am recording this series of videos related to electromechanical conversion systems. And one very important aspect when you are designing or selecting a electrical machine is the efficiency. And everyone in this video must understand that the efficiency of the electrical machine depend on the characteristic of the magnetic material. And basically, the efficiency is affected by what we call the active power losses in the magnetic material. And everyone here understand that the active power losses in magnetic materials are basically caused by two different phenomena. One of them, the induced eddy currents, and the others coming from the hysteresis losses. So today we have a very interesting and exciting example, numerical example, to calculate the active power losses in the magnetic material. So without further delay, let's start by reading this very interesting statement for the question Q1. So let's consider a sample of iron of density 7,800 kilogram per cubic meter. And we know for this sample that the constant Ke is 1.65 and the constant Kh is 150. Also, the Steinmetz index is defined by the letter X is equal to 1.8. So if we assume that the material is totally homogeneous, we want to calculate the eddy current losses PE and also the hysteresis losses. And everyone in this classroom must understand that when we see here PE, that means the total active power losses for eddy currents, and that means what? And here we have PH, capital letter H for hotel, and in this case that means the total hysteresis losses, in this case for hysteresis, and the unit is watt. And we know also that this sample is basically a 2 kilogram sample of iron. Now we want to calculate the eddy current losses and the hysteresis losses in 4 different cases. If you look over here, the 4 different cases, we are changing the magnetic density. In this case, the unit is Tesla, but also we want to analyze the effect of changing the frequency. And you can see that the frequency changing from low values like 50 and 60, low frequency AC signals, until reaching high frequency signals between 400 and 1 kilohertz. So in a minute you will see the solution process, but the first thing that you need to understand is that this is a very mechanic and repetitive solution. So I will go in details on the first solution, and then I will show you the steps for the others, because what I want to do is to get a conclusion at the very end of this problem. So without further delay, let's start the solution. And everyone that is watching this video and already attended to the classes must remember that the active power losses that we can find in a ferromagnetic material, they are basically caused by two different phenomena, hysteresis and eddy currents. However, when we are talking about those losses, we can talk about density losses. And when we are talking about density losses, that means that we are referring the losses to another unit. For instance, here, this beautiful equation over here will give you the active power loss density caused by the alternating AC signals and eddy currents. And as you can see, we are using the lower E letter, and that lower E letter means that this is a density. So as you can see, the units are watts per kilograms. So this equation over here will give you the possibility of calculating the alternating eddy current loss density, in this case in the units of watt per kilograms. And the equation is very simple because you can see inside this square we have the frequency and the magnetic flux density. And in the denominator you can clearly identify that is the density of the core material. Similar equation can be obtained for the alternating hysteresis losses density. So here we are using pH. And you can see over here that we are using lower letter h because again this is a loss density. And you can see here the beautiful equation, and in this equation the units are watts per kilogram. You can see that we have X in the exponent, and this is the Steinmetz index. You can see here the proportionality of the frequency. The denominator, you can identify that that is the density of the core material in kilograms per cubic meter. And inside the exponent, you can identify that is the magnetic flux density. So now what we need to do is basically use those equations to calculate first the alternating eddy current loss density, but using the numerical value for the first question, and in this case the maximum flux density is 0.6 teslas, and we are working with a low frequency AC signal, in this case 50 hertz. So the first equation over here, we get the loss density in units of watt per cubic meter. And as you can see over here, this is the alternating eddy loss density based in watt per cubic meter. And below we have the equation where you clearly identify the density of the core material. And using this equation, we can get the loss density in watts per kilogram. To be honest, this is the equation that I will be using in the following steps, because we want to obtain basically the alternating eddy loss density in watt per kilograms, because to obtain the total losses, we need to multiply for the case of 2 kilograms. So it's a very simple exercise of numerical substitution. You can see over here, this is KE 1.65. You can see here inside the exponent 50 hertz, that is the frequency, 0.6 teslas, and that represents the maximum flux density. And here in the denominator, you can identify 7,800 kilograms per cubic meter. So now, in order to obtain the total eddy current losses, what we need to do is basically multiply the loss density by the total weight. In other words, we are using here 0.1904 watts per kilograms, and we multiply by 2 kilograms, and this here is the weight, the total weight of the sample. You can see that kilograms cancel with kilograms, and at the end we obtain unit of watt. And as you can see, the total eddy current, and now we are using capital letter E, and that means this is the total eddy current power losses, and you can see 0.3808 watt. So is the first part of the question A, because now we need to calculate, we should calculate the hysteresis losses for this very specific case. And that is what I will do now for you. What I will do now is I will calculate the hysteresis, the total hysteresis power losses for this case of 0.6 Teslas and 50 Hertz. So again, is very simple the equation you can identify on the top. This is basically the loss density, alternating hysteresis loss density. If we use the equation on the top, you can see this is watt per cubic meters. Or if we use the equation here, and this is the equation that I will be using for the rest of this example, if we use this equation, you can identify that the units are watt per kilograms. So you can identify is a very simple solution, We substitute the value of KH, in this case 150. We substitute the value of the frequency used during this test, 50 Hertz. Here you identify the maximum, and this is the maximum flux density, 0.6 Teslas, and you can identify the exponent 1.8. The denominator, as you can see clearly here, delta I, and that represent the density of the magnetic material, in this case 7,800 kilograms per cubic meter. So at the very end, we obtain here the hysteresis loss density, 0.3834 watts per kilograms. And what we need to do to obtain the total hysteresis power losses, pH, in this case, H is a capital letter. And when we are using capital letter, you must remember that represent the total losses, and the units coming from the total losses are watts. So multiplying 0.3834 watts per kilograms multiplied by 2 kilograms, that is the total weight of the sample, we obtain here the total hysteresis power losses, 0.7668 watts in 2 kilograms. Something that is interesting, and I want my students to reflect, I am putting here the two different losses for 0.6 Teslas and 50 Hertz. You can see here eddy currents are probably around the half of the hysteresis losses. What I am trying to tell you is that for this magnetic flux density and very specific frequency, you can see how the hysteresis losses are higher than the eddy currents. So now what I will do is I will move to the next case, and I will do that extremely fast because now we understand the equation that we need to use. And now what I will do is straight away multiplying by the weight. So if we use this equation over here that I presented before, 1.65 is KE, 60 Hertz and 1 Tesla, because this is the case B, and 7,800 kilograms per cubic meter. So finally, we obtain the total eddy currents, and you can see 1.52 watts. Similar situation can be used for the case of the total hysteresis losses. And in this case, we have here the equation. It's very simple, a numerical substitution. KH is 150. The frequency in this case is 60 hertz. You can see that the magnetic flux density is 1 Tesla. Steinmetz index 1.8. 7,000 kilograms per cubic meter is the density of the magnetic material, and 2 kilograms over here, the total weight of the sample. So as you can see over here, now we have the hysteresis losses for the case B, and this is 2.3 watts. Now, if you compare, again, the hysteresis losses are higher than the eddy current losses. However, they are not so high compared with the eddy currents. Let's do now the question C in order to keep moving in this solution. And as you can see now, the frequency that we are using on the question C, the frequency is 400 hertz. And the magnetic flux density in this case is 0.7 Tesla. So again, using the same equation that we already defined doing the numerical substitution, now we can see something quite interesting. You can see over here that this is the total eddy current power losses, 32.16 watts. And here we are using the equation, the same equation that we used before for the hysteresis current power losses. And now we have here the solution for the hysteresis. Now you can see that when we are using 400 hertz, you can see the eddy current losses are 33.16 watts. And the hysteresis losses is only 8.09 watts. So now eddy currents are higher than the hysteresis losses, and in this case, this is for 400 hertz. However, the final question, and probably the summary and the closing of this example, is quite interesting. And the reason is that now we are planning to answer question D, and in this case, the frequency is 1 kilohertz. So now let's use the same equations that we has been discussing before. This is the equation for the eddy current losses. This is the equation for the hysteresis losses. But now we are using a lower maximum magnetic flux density, 0.5 Teslas, and we are using 1 kilohertz. So when we numerically substitute in the equation, now you can see here the total eddy current losses, 105.7 watts. And here you can see the hysteresis power losses, and in this case is 11 watts. So as you can see now, the hysteresis losses is almost 10 times compared with the hysteresis losses. Eddy currents are higher than the eddy current losses. So to close this example, and to be honest, this is the most important part of this exercise, we got the numerical results for 4 different cases. And in those 4 different cases, what is important to see is that those 2 cases, A and B, they are for low frequencies. And this is 50 and 60 hertz, the classical frequency that we use for electrical power systems. But here we have the frequency for 400 to 1000 hertz. So if you look over here, case A and B, you can see that the hysteresis losses are higher than the eddy currents. And that repeat again here on the case B. However, when we go to higher frequencies, for instance, 400 hertz or 1 kilohertz, I believe it's clear to all my students that now eddy current losses are higher compared with the hysteresis losses. So in this example, the idea of having 4 different cases, A, B, C, and D, is that basically we want to show you how important are the eddy current losses and the hysteresis losses. And depending of the frequency that we are using, and depending of the magnetic flux density that we are using, so one of them can be higher than the other. So I hope you enjoy this very interesting video, and I highly suggest that you go at home and you repeat this example with other frequencies and other magnetic flux density, and reflect about the effect of the frequency and the magnetic flux density on the eddy current losses and the hysteresis losses. So, well, sadly, we arrived to the very end of this video. It has been longer than expected, but I hope you enjoy it, and especially that you are enjoying this very important learning experience about electromechanical conversion devices. So I will see you at the next video. Thank you very much for watching. If you have any question, please drop an email or also contact me directly, and I will be extremely happy to support and help you. Thank you very much for watching, and I will see you at the next video. Bye now.